Picture a smooth, icy hemisphere. A tiny block sits right at the top. You give it the slightest nudge and it starts sliding down. Now here's the question. Does it slide all the way to the bottom? Or does it fly off somewhere along the way? And if it does leave the surface, at exactly what height? Pause and think about it. What does your gut say? Let's set up the problem carefully. Here's our hemisphere of radius r, and here's the block at some angle theta from the top. At this position, two forces act on it. Gravity pulls straight down with force mg, and the surface pushes outward with a normal force n. As the block slides lower, something interesting happens to that normal force. Watch the normal force arrow as the block slides down. It's shrinking. At the very top, the surface supports most of the block's weight. But as it picks up speed and curves away, the surface has to push less and less. The moment the normal force hits zero, the surface isn't pushing at all. That's when the block lifts off and becomes a projectile. So our job is to find exactly where n equals 0. Remember circular motion from physics class? Anything moving in a circle needs a centripetal force, mv squared over r, pointing toward the center. On this hemisphere, that inward force comes from the difference between the inward component of gravity and the outward normal force. So we need two ingredients, the speed v at angle theta and the force balance in the radial direction. Let's find the speed using energy conservation. No friction means no energy loss. At the top, the block has zero kinetic energy and potential energy mgr. At angle theta, the height is r cosine theta, so the potential energy is mgr cosine theta. Set them equal. 1/2 mv squared equals mgr minus mgr cosine theta. The mass cancels from every term. That's a huge clue, the mass doesn't matter. Factor out gr, and we get v squared equals 2gr times 1 minus cosine theta. That's our speed formula. Now the force equation along the radial direction, pointing toward the center. The inward component of gravity is mg cosine theta. The normal force n pushes outward. The net inward force provides the centripetal acceleration. So mg cosine theta minus n equals mv squared over r. At the moment of liftoff, n equals 0. The surface stops pushing entirely. So we get mg cosine theta equals mv squared over r. Mass cancels again. Now substitute our energy result into the force equation. G cosine theta equals 2g times 1 minus cosine theta over r times r. The r cancels, and g cancels from both sides. So cosine theta equals 2 minus 2 cosine theta. Collect the cosine terms. 3 cosine theta equals 2. And there it is. Cosine theta equals 2/3. This makes sense. 2/3 is between 0 and 1, so theta is between 0 and 90 degrees, somewhere on the upper half. The height above the ground is r cosine theta. And since cosine theta is 2/3, the block flies off at exactly 2/3 r. Not at the top, not at the bottom, at precisely 2/3 of the way up. And notice, it doesn't depend on the mass or on g. Whether this hemisphere is on Earth or on the moon, the block always leaves at the same angle. So the answer is h equals 2/3 r. The key was balancing energy conservation with centripetal force, finding where the surface can no longer keep the block on its circular path. This same physics governs roller coaster loops and water sliding off a dome. If you enjoyed this, like and subscribe for more.